Okay. All right. Well, we make an announcement. As you all probably heard, there's no math club today because we do this first Friday thing, and if you're new to it, I think April said 5. It's usually kind of a good idea to get out here a little bit earlier if you don't need to talk about traffic. But if you like the parade, then maybe you're happy to be traffic. You will also be very brokenhearted to hear that I'm not quite done with your next homework assignment. I was polishing that as a student, so I will post that. I'll probably post that over the weekend, and then I'll talk about the problems on Monday. If I forget to do that, give me a holler, or get to talk about it in the class next. Okay. So the last thing we were doing was we were talking about localizations. I've been focusing mainly on domains. One of the problems on your next homework set will be to sort of hash this out a little bit in the case of zero divisors. Our set multiple closed. Then we have this thing to define RS. I don't think I stated this last time. You got to be a little bit careful. These are sort of equivalence classes, right? You know, when you're in grade school, you reduce fractions, 2/4 is 1/2, right? I mean, really, is 2/4 really equal to 1/2? Well, as an ordered pair originally, no, they're not. But what you do is you clump them all together in an equivalence class. And we actually say that over S, let me say equivalence class is equal to. So here's my actually, let me set up like we say that the ordered pair, or R over S, is equivalent to R prime over S prime. If and only there exists S double prime and S such that R S prime minus R prime S. Now I kind of skimmed over this a little bit because let me point out that if your playground is an integral domain, so R is an integral domain, then there are no non-trivial zero divisors. And so this statement right here, if you're in a domain setting, means one of these two animals is 0. Well, this one can't be 0 if you assume that your set S doesn't contain 0, which I think I said last time. So if you're a domain and your set doesn't contain 0, then you're left with this, which is the old familiar way of telling the fraction the same. It means the cross multiples are the same. That's essentially it, right? And the addition was thusly and the multiplication also. Like that. We also had this terrible notation that if P in R is a prime ideal, then S or minus P is a saturated multiplication of both step. In fact, there's a more general statement we have that if you have S as the complement of the union of primes, it's saturated multiple set. But in particular, the notation is in this case, we have P. I'm sorry, R localized P is let's find the RS with S is confidence. Now, I kind of alluded to some of this last time. But let me do a couple of examples. So the last thing I think we did last time was example 1.5.2. Let me kind of use that to kind of allude to things here. So let's look at the easy ring. I like easy. And let P the ideal generated by 2. Well, actually, let's just, I mean, this is a 9500 bus, so let's consider, let's do it more general on P, generated by P, where P is a non-zero prime. So I'm gonna use this to kind of bootstrap my way to a good example. So let's look at R localized. This is the set of A over B, where B is not in this idea. Now, I claim that P, CP is the unique maximal ideal. I claim that PZP is the unique maximal ideal of this. And basically, PZP, this is just all multiples of P. And so, I mean, you can actually think of this as P over B. Actually, let me not say this, but let me say gamma over B. The gamma is in an ideal generated by P. And B is not in an ideal generated by P. So in other words, PZP is basically what you have in Z localized as P is fractions whose denominators are relatively prime to P. And PZP, what happens is you get this ideal where the numerators all have multiple P in them. Everybody okay with that? Is it clear to everybody that this is in fact an ideal, right? If you add two fractions whose denominators are relatively prime to P, and whose numerators actually both have a factor of P, then again, the sum is still from there. And it just follows the rules of the way we add this, because the numerator is a linear combination of numerators, so it has to have a factor of P. It's also, isn't it also clear that it's an ideal, right? Because if you take a fraction whose numerator is in P, multiply by any other fraction, that numerator is like a vacuum cleaner. It sucks it into having a multiple P. Huh. Okay. But I want to show that it's maximal. And I want to show that it's the only max. First question, why is this ideal maximal? And by the way, of course, proving it's maximal will prove that it's prime as well, right? Any ideas?
Take anything wrong.
Okay, yeah, that smells good right there. So suppose you have let's say A over B, where A and B are not in, do not have multiple, not in, don't have multiple. B. And where can we go with that? Yes.
A unit now, because.
Okay.
We have denominator, that's gonna cancel out.
Okay, so in particular, actually, that's a great observation. If I have PCP, and then I stick this in, which is the form of anything that's outside of this is a unit. Because actually, I can turn this fraction upside down, can I? Because the numerator has a factor in it, right? So, in a very simple way, this is all of delocalized P, because this now has a 1 in it, right? Right? Because it's got a unit in it, right? So this is max. Okay, why is it the only max? I think it's the same reason, isn't it? Essentially, right? So now suppose there exists another maximal ideal. Probably if it's distinct, well, let's say if is not equal to P0 plus P, then there exists X in M minus PCP. But of course, anything, as we've observed before, must be a unit. So X equal to A over B with A, B not in, not a multiple of P and Z. Therefore, X then units of 0 plus P, which is 200. So this thing basically has one. And here's what's happened. If you look at Z, if I were to draw the prime ideals of this, I'd have a heck of a time. There's actually infinitely many, and this is, if I were to diagram the prime ideals, it might look something like this. 0 is contained inside every prime ideal, and there's sort of like this, it looks like a little chia pet, right? I mean, you got the little hairs growing out of it. There's 2, 3, 5, and here's our prime ideal. When I localize, when I pass to the localization, what happens is it focuses right here. And it turns all the other prime ideals into garbage. They're all units now. And so what I'm left with is going from this kind of confusing thing with a lot of hair on it. I get to a ring that has a unique maximal ideal, and then it's got this little 0 in it, and that's how you go. And you can extend this, right? So for example, let me kind of extend this example. Suppose that I want to study my favorite n primes. So let start this 0. Well, here's what I can do actually. Look at I can take this collection of prime ideals, P1, P2, all the way up to Pn. I can look at the union of all these prime ideals. Notice that this union contains the primes P1, P2, all the way up to Pn. They're in the union, and it contains no other prime, right? For example, if P1, P2, up to Pn are all odd, there's no way this contains two. It can certainly contain even numbers, but it can't contain two. Everybody agree with that? And if you let S equal, if you let this be the complement of S, so S is the complement of this, then Z localized at S is singular. And in fact, what's going to happen is you just isolated these in primes. So what Z localized at S now looks like, if you're going to draw the prime ideals, it's got 0, P1, P2, because the rest of the primes that aren't in that list, which is all the primes except for P1 up to Pn, are now in the complement of that, right? So they're in the multiplicative set you're localizing. So effectively, what have you done? You've taken every prime that's not there and allowed it to be a denominator, right? So you turn all those other primes into units. It destroys all those other prime ideals, turns them into the trivial ideal, and you're left with that. So I'm going to give you a theorem that generalizes this. Note if R is a domain and then we can think of this localization as a ring between R and its quotient field. This brings me to the following definition. Let R be a domain with quotient field any ring T with it's called an over. So when you hear the terminology over ring, it's very special. It is a ring that is contained between the original ring and its quotient. Notice that my previous result says, or the previous observation here says, that if you have a localization, right, R localized at S, it is an overring. What question am I going to ask next? Read my mind. Right. Are there other? So let me give you a theorem to tantalize you a little bit, and I'm actually probably going to put this on. I think it's on the next set. Theorem. Theorem 1.5. If R is a principal ideal domain, and P is an overring, of R. Then P equals RS for some multiply closed. That S and R. So, this theorem's not too bad to prove. But what it says is if your actual principal ideal domain, and you have an overring of your principal ideal domain, it's automatically a localization. There is some magic set that you'll be able to find in TSRS. You might think of an example. Is this always true? Do I need to hypothesis PID? Well, I'll prove it guarantee it, but I need that hypothesis. I don't think. But it's not true in general. There are overrings that aren't localizations. Anybody think of a way might do that? I'm not going to go through all the details of this. This will be something that you can think about because you're all energetic grad students. But here's an easy. Okay, so just take a polynomial. By the way, it better be two variables. I'm going to do polynomial because a polynomial, if I'm going to give you a counterexample, polynomial ring in one variable over the field is PID, right? So I'd be hard pressed to find exactly here. But with two variables, I can do a little bit of nastiness. Let T equal now, let me make it clear here. The function is that round bracket line. What I mean by that is all rational functions in X and Y. So here's an intermediate ring. We've seen this kind of example in a different context before, but this is a useful construction. What I've done is I've taken this ring here, fxy, but I became unsatisfied with just having x and y, so I was throwing these new rational functions, y divided by x, y divided by x squared, and so forth. They can just add every one of them. Now, this ring has some interesting properties. Number one, it is not Noetherian. And in fact, the ideal generated by all these rational functions in here is not a finite generated ideal. Again, I need two variables for that because any overring of a PID is Noetherian. It's not defined. So I do need two variables for that. This is not Noetherian, and it's not a localization, right? It turns out if you localize a Noetherian ring, you get a Noetherian ring. So that's one quick proof of that if you believe it's not Noetherian. Another proof, if you like getting your hands kind of dirty, is basically this is trying to put X into a multiplicative set. You're trying to let X be a denominator, aren't you? But notice it's a fairly easy computation to show that 1 over X is not in this range. And so X is not really in a multiplicative set. So there is no multiplicative set actually. That's very fast to lose, but you might think about why this is true. This is not a localization. Okay, any questions? Okay, so let me give you like sort of the big, if you will, localization correspondence. Oh, yeah. So here's a little, sorry about this segue, so I'll bring these folks into it too. I am going to propose a topics course for the spring. And what I'm thinking about doing is a course in factorization / algebraic number theory. Sort of, I mean, it's a selfish course. course. It's stuff that I'm interested in my research, but it'll be kind of something that we'll do a little bit of number theory, especially toward commutative algebra factorization and some factorization theory. How many of you might be interested in that? Perhaps. Okay, if you wanted, and of course, for the topics course, I can also take votes as well. But for me to get this thing to run, I'll probably have, there's a couple things I have to do. I'll make up a syllabus, so I'll make up some garbage or whatever that's in the theme of whatever this is. And number two, the point will have to be, is anybody actually going to take your stupid course? Jim, they usually have to list of students. So I was thinking about putting a lot of you on that list. So when you do me a favor and email me, it's okay for me to, this is not, we're not getting married here. It's not mean that you have to take this course, but it is that you're interested in the course. Okay, so send me an email if it's okay with you for me to put you on the list of potential students. And same for you out there in Etherland. Okay, so here's the theorem. Let R be a commutative ring of identity, S a multiplicative closed subset of R. Subset. And here I'll see something that's not this. I don't want to turn anything into zeroing. Then there's a one-to-one correspondence between prime ideals of R that miss S and prime ideals of R localized S. Then there exists a one-to-one correspondence. Prime ideals of R that miss S, and precisely what I mean by the prime ideal missing S is that the prime ideal intersect S is nada, is that they miss empty set overlap. And the prime ideals of our localized. And I'm going to show you how that correspondence works. So let me kind of draw a picture of it, if you will. So what you have is you have a set of primes P in R such that P intersect S is empty. And it corresponds to our localized S. And the way the correspondence works is the way the correspondence works here is the prime P goes to P localized S, which is the same thing as so it's basically, here's another way to think about it. This theorem is true in general, but here's kind of a good mnemonic device way to think about it if you're in domains is these are domains, then this is an overring, so it's a bigger ring that contains it. And what this is this is the ideal in this bigger ring, it's just generated on the set P when I lift it up there. Just take everything in P and use that as a generating set up here. However, this is true in a more general setting. What happens in the localization is this S, sometimes we say it blows up. This turns in, all these become units up here. Right, and then there's I do here. Yes. I will leave that as kind of an exercise to do, because actually, once I tell you how the correspondence works, it's fairly easy to verify that if this is prime, then this is prime, and one-to-one correspond. In fact, yeah, you might think how the correspondence works. How do you get from here back to here? Again, for domains, it's a little easier to picture, because the way you get back here for interval domains is you can just intersect. Okay, any questions? So let me, and I was thinking today, when I was thinking about this class, I was like, am I being a little premature with this? But I don't think I am. I'm going to talk about valuation domains a little bit later, but I want to introduce them now. This is an important concept. So valuation domains, which is what we're going to introduce. So how many of you have seen algebra 2, the field theory, the Galois theory? So you all know what it means for something to be algebraic. Well, there is sort of a shared concept with domains, a generalization of algebraic called integrality. The only difference is we demand that the polynomial be monoid. But this is very central. This is central both in commutative algebra and in its predecessor number theory. Algebraic number theory is based a lot on integrality. Valuation domains are very incredibly important here because, for example, there's one big theorem we're going to get to that says if you have an integrally closed domain, it is the intersection of the valuation over, right, which is sometimes very useful. Here's another important thing, and that is if you have any, say, integral domain, your favorite integral domain, and you've got your favorite ideal in there, proper ideal, so not the whole thing, then there is a valuation overring of that domain where your original ideal survives. That means it doesn't blow up into the whole ring. And that's actually a very important thing too. And the fact that the ideal survives in this ring is important as well, because if you look at the definition of valuation domain, you can see that one doesn't expect a lot of ideals to not blow up into everything. So let me, without further ado, make the theorem. Let V be an integral domain. The following conditions are. Number one, for all AB, well, 0 not equal to anything in B, A finds B or B finds A. So you pick two random non-zero elements, one of them has to divide the other. Wow, right? I can name one kind of ring this is true for, a field, right? A field is even stronger because if you get any two non-zero elements, both of them divide each other, right? But here, one of them has to divide the other. The first thing I thought when I saw this is like, is there something like this that isn't a field? Two, for all so I should introduce that in the definition. Let K be the quotient field of D. For all omega and K, omega or omega inverse is in D. By the way, before I put the last one down, let's think about this just for a minute. Okay, so I was a total smart aleck. He said, well, okay, certainly a field will work for this. Now, once you leave fields, what is everybody's favorite example of a ring, right? I mean, I consider the integers as the prototype to everything. It's the prototype in number theory, it's the prototype in commutative algebra. In no freaking way is this true for the integers, right? Take 2 and 3, right? Neither one of them divides the other. Look at the quotient field. By the way, it's fairly easy to see that these two conditions are equivalent, actually. But take the quotient field of, take the rational numbers and take 3 halves, right? Neither 3 halves nor 2/3 is an integer, right? So the integers are very far from satisfying this, but of course the rational numbers do. My question, can anybody give me an example of something that satisfies either one of these conditions because they're equivalent? That's not a field. And yes, the ring has to have one.
Power series.
Power series over,
So maybe more interesting over periodic integers. Or maybe over.
no, it's not over the p-adic integers. That, yeah, power series over p-adics won't be. But the p-adics by themselves will be.
Yeah,
And the power series by itself will be, as long as the power series is over.
maybe over Q.
Yeah, sure, that'll work, any field you like. That's actually a good garden variety example there. So he said, the integers. Well, maybe we'll get to this, but to be sure that I talk about the p-adic integers, or to increase your chances, be sure and email me and tell me that you want to talk in this course in the spring. This one actually, you're right. This is an example one. A power series ring over a field in one variable. This will have this property too. And of course, clearly this isn't a field, right? Because X is not invertible. Right? Let me see why this is true. And this is kind of a nice flashback to, this is a nice flashback maybe to 8510 or something like this. No. Yeah. F of X is an F power X. Then F of 0 is not 0 if and only if y'all remember that the power series over a field that, in fact, in general, if you have the units in a power series ring are just all power series whose constant term is a unit, right? So for a field, all you need is for the constant term to not be 0 and its unit. Everybody, is that all one with those with y'all? So this actually allows me to do something really groovy. And that is if f of x is not 0. So suppose this is not the 0 power, then f of x is equal to a n x n plus a n plus one x n plus one forever, for a n not zero. Right? So what I've done is, if you have a power series that's not zero, I've just sort of written down a n is the first non-zero term. And this is a unit. Right, because a n is not zero. Right, it's just power series of the field. And so what this allows me to do, actually, which is kind of cool, is the following. In f of x, elements look like I can classify it two ways. Zero, there's one element, and two, x to the n becomes a unit, where n greater than zero, u, and u. Okay. Because any non-zero, I can write that way, which is x n. So if I walk up to these on the street and give you two non-zero power series over a field, one of those has to divide the other. And which one? Well, if n is the small exponent, then this is the one that divides that. If n is small, then this divides this. And if it's a tie, they both divide each other. Okay. So this is a non-trivial example. Anybody think of another one?
I think you can consider a polynomial ring quotient equation defined by a smooth curve. For example, qxy quotient x squared plus y squared minus 1. And you use any prime ideal to localize the ring.
Yeah, then you look, yeah, that'll work too. And that's a good example. That one will work as well. See, localize. And here's the reason. If you have two non-zero elements, very similar to this. In a similar fashion to this, you can prove that any two non-zero elements look like p to the n a1 over b1, p to the n a2 over b2, where a1, b1, a2, b2 are relatively prime to b. Because notice b1 and b2 have to be relatively prime to b by the way we construct the localization. And I can just keep pulling factors of p out of the numerator until I exhaust them all, until I get it down to where a1 has no factors. So again, it's the same argument. So, and of course, n and m are greater than or equal to 0, whichever exponent is smaller one divides the other one. All right. But there are others. There are many, many others, right? Even though this seems like a simple definition. I can actually build valuation domains. I might tell you heights, I guess. So for example, in the so in fxy, that's a maximal ideal, that's a prime ideal, and that's zero ideal, which is prime, right? We often say that x is a type 1 ideal, type 1 prime ideal. because you can't squeeze another prime in between them, right? And in fact, X is irreducible, so you can make that kind of argument, right? I can build valuation domains that are not fields and have no height on prime. That is to say, given any and any prime here, I can find another prime in between, no matter how small, even under these assumptions here. The last one in here, 3, here's an equivalent condition. D is quasi-local. And my reminder is that means that it's got a unique maximal ideal. And every finitely generated ideal is principal. So any ideal that only requires finitely many generators only requires one. Notice this does not mean that every ideal is in fact finitely generated. In fact, it's not. And in fact, since I'm on the subject, I'll give you the following definition. Well, a domain satisfying these conditions. In fact, all it has to do is satisfy one, and then it satisfies them all. It's called a valuation domain. We're also going to approach this from another point of view, because it turns out a valuation domain has something on it called a valuation, and hence the name, right? It's not clear at this point why are we calling it a valuation domain. Hopefully I'll make that clearer later. Definition. A domain R is Bezout, and there's all kinds of French stuff on this. I don't know how it works, but a domain is Bezout if every finitely generated ideal is principal. So notice that a Bezout domain is a generalization of a principal ideal domain, right? A principal ideal domain is Bezout, but Bezout can be more general than this. So it's got this weird property that it may have ideals that are not finitely generated, but everything that can be finitely generated can actually be principally generated. So a valuation domain is a quasi-local Bezout domain. They're equivalent. Bezout domains are all over the place, and in fact, an important example of Bezout domains that aren't PIDs is the ring of entire complex example. That's actually a Bezout domain that has very strange properties. Here's another Bezout domain, the ring of all algebraic integers, right? So that is, those of you that are number theory fans, if you take the collection of all complex numbers that are the root of some monic polynomial coefficients in the integers, this makes a big, huge ring. It's got a huge, in fact, every prime in the integers is contained in infinitely many maximal ideals from this. It is an example of a Bezout domain that is in fact, it's a Bezout domain. It's not. Okay, I think that's kind of a good place to stop for now. Are there any questions? Any questions out there? All right, well, you all enjoy your first Friday. Have a great weekend, and we will see you next week.